Okay, we're recording. So it is October 24th. Today we will be discussing three-dimensional geometry as a continuation of what we worked on last week. Now, just before we begin, I would like to talk just a little bit about something called Khan Academy. I'm not sure if all of you have Khan Academy, but it's a very useful tool. I assume that would be Miss. So, before we start today's lesson, I'd like to talk about Khan Academy just a little. Khan Academy is a very useful online tool to help you learn not only your math, but other subjects such as your reading and writing and science, etc. Because this is a program for your benefit, part of me teaching you is to give you lots of academic tools for you to use later on in college. Miss Delana Marks, we are talking about Khan Academy just before today's lesson. So,
okay, sir.
So I think I'd like to start off. First off, how many of you have Khan Academy? None of you? All right. Let's see.
Sir, I have seen Khan Academy.
Okay. I would suggest that all of you get a Khan Academy. I am sharing my screen. Can everybody see my screen? It is Google.
Yes, sir.
Okay, so here's Khan Academy. And Khan Academy is good because it has a little bit of everything. I have a pre-done class here, or a pre-made account here, which I use to give some resources to a second grader before. Here they have plenty of activities and video lectures on topics in math and plenty of other concepts. So I don't believe you necessarily need to make an account, but I think it would be more convenient if you did. Khan Academy costs no money to get, and it is very, very helpful for your classes, because if later on when you take college, you will be learning mainly through lectures, such as what I have sort of been doing for all of you so far. So if you are the type of student who does not learn well from lectures and only occasional one-on-one experience, Khan Academy is very good as another resource that has more learning options. So to spell it, I think the link is right on top here in the search bar. It is Khan Academy. If you look it up, it'll show up because it is a big site, and I very much recommend it to you. Does that sound good, everyone?
Yes, sir.
Okay.
Yes, sir.
KHAN Academy. So it is nice that we have many people today. I know that not everybody is able to come every week because of internet connection issue, but have all of you found the YouTube channel helpful so far?
Yes, sir. Yes, sir.
Very good. So hopefully all of you have seen the lesson from last week. Before we go straight into 3D geometry, I want to start off by doing a little bit of review of what we did last week. We talked a little bit about lines. So there are three types of lines. Would anybody like to tell me what each of these are called?
A line, array, and a line segment.
Thank you very much, Mr. Nathan. So this would be a line. This would be an array. And this would be a line segment. Miss Alicia, would you be able to tell me what these arrows mean and what these dots mean? If not, Mrs. Alicia, does anybody happen to know other than Mr. Nathan?
Excuse me, sir. Can you please repeat back the question for me?
Very good. You're not seeing very well with the marker. Okay. So we have three types of lines here, which we reviewed last week. We have a line segment, array, and a line. As you might be able to see, the line segment and the array each have dots or arrows at either of the ends of them. Would anybody happen to know what the difference is between the dots and the arrow? Very good. Mr. Aryan has noted that the arrows go on forever. So if the arrow goes on forever, would anybody happen to be able to figure out what the dot would then mean?
Sir, on point.
Very good. So the dot represents a point. Now, a point represents a single place in space. So this means that if a arrow means that the line goes on forever, then a point means that the line must end or begin at this dot, at this point. In this case, array begins at this dot and it goes on forever in a line. A line segment begins somewhere and ends somewhere. A line is special because a line, you can neither tell if it begins anywhere or if it ends anywhere because it goes infinitely in each direction, which means that if we were to say it had a beginning, it would have to be somewhere on the line, and we would have to specify it. In calculus or math in general, we have such a thing as a number line. I would hope that everybody is familiar with it. Would anybody tell me, does a number line have a beginning?
Yes, sir.
Okay, where would it be?
At 0.
Very good. So our number line begins at 0 because that is how we start counting by our real numbers. Now tell me, if we had one of these lines that described all positive numbers, would it be a line segment, array, or a line? Ms. Delana, would you happen to know?
Sir, can you please repeat that?
Very good. If we were to draw a line that represents all positive numbers, would it be a line segment, array, or a line?
Excuse me, sir. A line? Is there a line?
Well, let's look at a line. A line says that it goes to the left forever and goes to the right forever. Positive numbers go on forever to the right. We know that because you keep counting up. Ms. Delana, what happens if we keep going to the left forever?
That would be negative numbers.
That's correct. So this means that a line that describes all positive numbers can't go to the left forever then, correct?
Yes, sir.
But it can go to the right forever, correct?
Yes.
So which one of these can go on forever, but starts at any particular point?
Sir, array.
Very good. So a line that describes all positive numbers or whole numbers if we start at 0, we say that it goes on forever as array because it starts roughly at 0 and you count 1, 2, 3, etc. Could anybody tell me what would it be if we had a line that described all negative numbers?
A line segment.
Okay, well, let's look at it. A line segment is a line that begins and ends. So it is a finite length. So, Mr. Nathan, a line segment says that it only goes to the left by a certain amount and only goes to the right by a certain amount. What happens if we go on to the right forever? Mr. Nathan.
Sir, that it won't stretch out too much.
I don't quite understand, Mr. Nathan. So, Mr. Nathan, I'm wondering, if we had our line that described all the negative numbers, if we went to the right forever on the number line, what happens?
Then it won't be a line segment.
Well, no, Ms. I'm not saying anything. I'm just asking, Mr. Nathan, what happens on the number line when we go to the right forever?
We keep counting on and on with the positive.
Very good. We reach the positive numbers and we keep on going. So if it was a line that described all negative numbers, we know that it would have to end close to 0 because that's about where the last negative numbers are. Mr. Nathan, what happens if we go on to the left forever?
It just goes on and on.
On for positive or negative numbers?
For negative numbers. On and
Very
on for
good.
negative numbers.
Thank you. So, Mr. Nathan, if we know that the negative numbers eventually get close to 0, but they count on forever in the negative direction, which one of these lines would that count as?
Can you please repeat that?
Very well. If we know, because we said that a line that describes all the negative numbers ends at 0, but it goes on forever when we count with negatives, which one of these lines would the negative numbers count as? So it has to be whichever one of these lines begins somewhere but goes on forever. Which one of these would that be, Mr. Nathan?
Array.
Very good, Mr. Nathan. So a line that describes all the negative numbers is array that points in the opposite direction. So now we have our number line where we have an array that describes from 0 all the positive numbers and a negative array from which describes all the negative numbers before 0. If we put these two arrays together, does this become a line if we include both of these arrays? Anyone?
Yes, sir.
Very good. Because we go on forever to the left and we never stop even at 0, even though both arrays begin there, because they begin there, every number in the entire number line is accounted for. So that means that this is a whole line. Now, if we did not include 0 and we just said the negative numbers and the positive numbers, would this still be a line? Anyone? Perhaps Mrs. Ariel?
Sir, I'm not sure.
Okay. So Miss Ariel, if so we have two arrays, one describing negative numbers and one describing positive numbers. This time we took out 0. If we take out 0 and we're left with these two, in this case they would be rays because they stop just before 0. Do we have a full line that goes all the way in the left and all the way to the right?
No, sir.
Very good. Why?
Because it won't have a 0 to be in the middle to show whether it's negative or positive.
Very well. I mean, very good. So what the concept that we're describing here is called continuity. Does anybody happen to know what continuity is?
No, sir.
No, sir.
Very good. So we have continuity. Now, one of my favorite math teachers told me that the English language loves to take a lot of words from math and they turn it into other concepts. Does anybody see any words in continuity that might look familiar?
Continue.
Very good. We see continue in the word continuity, and because hello?
The last piece just now look like infinity.
Infinite, maybe. I guess maybe in a sense. If we say that in the beginning we have continue, and in the end the suffix we have ity, and we said that that's similar to infinity because annuity sounds a little bit like infinity, we say that it continues to infinity. So this is what the word continuity means. It continues to infinity. And what this means is that because it must continue, a line has to be continuous. That means that it has to include every single number from all the way to the left to all the way to the right. And because here we have 2 rays and it's missing 0, it is not continuous because it does not continue to infinity. Because if we started here and we want to continue to infinity in the left direction, it does not continue at 0. This is an extremely important concept for later. But for now, we are only reviewing geometry at the moment. Does anybody have any questions?
No, sir.
No, sir.
Okay, sounds good. Now, when we describe lines, we say that lines are 1D. Does anybody know what this means? Very well. When we see 1D, I'd like to note that we are going to continue to 3D. If we go back to shapes, we said that shapes like squares and circles were 2D. Does anybody know what 2D is?
Two-dimensional.
Very good. 2D means two-dimensional. Yeah. So what does two-dimensional mean? Does anybody remember what a shape needs to do to be called a shape?
So have equal sides.
Can you repeat that, please?
They must have equal sides.
Not quite. You're thinking of a regular shape. Anything that follows certain rules can be a shape. This is a shape. Can anybody tell me what you need to do to be a shape?
So
You have
length
to be
and width.
two-dimensional.
I'm sorry. Mr. Nathan, you are correct, and we have said this. Mr. Aryan, I believe you were about to say something.
Sorry, can you please repeat back the question?
Mr. Aryan, I am simply asking, what do you need? What are the rules to be a shape? We said that a shape must be two-dimensional, but we're trying to figure out what does two-dimensional mean. So we're going back to saying what a shape is, and we're saying, what do you need to do to be a shape?
Sir, to be a shape, you need length and width, but no depth.
Okay. A shape has, in a sense, length and width. What I was hoping that any of you would have found in your notes is that a shape must have closed sides or closed perimeter. So that means all of the outside of this shape must be closed, so there are no openings like this. And the shape must be flat. I specifically wanted to say flat, but saying length and width is good enough. So when we say it must be flat and it has length and width means that the shape goes in this direction and in this direction, vertical and horizontal. That's what a shape is, because each of these lines is what we call a dimension. Now, in today's time, this might be a little confusing because pop culture has basically confused everybody on what a dimension is. Sometimes people think that a dimension means a universe, like our universe. But what a dimension means is more akin to direction. So 2D means two-dimensional, which means it is two-directional. Does anybody think they understand what it means to be two-directional?
Yes, sir.
Okay, Mr. Nathan, how would you describe two-directional?
Like how all the shapes that we know are plane shapes that are flat, it goes only two directions.
Very good. Because we know that a shape only points in two directions. That means if we saw our shape in real life, it would be completely flat because it only points in two directions and it does not have any what we call depth. That's why we draw on the whiteboard. Anything that we draw on the whiteboard is a shape because it is flat. It does not stick out of the whiteboard. So if a shape is two-directional because it only points in two directions, what would it mean that a line is one-dimensional? Anybody other than Nathan? How about Mrs. Ariel?
Sir, could you repeat the question for me?
Absolutely. Miss Ariel, yeah, we said that a shape is two-dimensional, or in other words, two-directional. And we said that because a shape is flat, in a sense, that a shape points in two directions. That's what it means to be two-directional. If we say that a shape is two-directional because it points in two directions, what can we say about a line that is one-directional?
Sir, it's parallel.
Not quite.
Sir, can it point in one direction?
Very good. That's exactly it. So one-directional means that it points in one direction. So a line is one directional because it points in one direction. We said that a shape is two directional because it points in two directions. Could anybody tell me what they think 3D means?
Sir, three-dimensional.
Exactly. So 3D means means dimensional, which means three directional, which means point in three directions. Does anybody have any questions so far?
No, sir, I understand.
Okay, so a 3D, whatever it is, has to point in three directions. Would anybody happen to know what something like that would look like?
A triangle.
Cube.
Mr. Arya, not quite a triangle. A triangle is a shape, so it is two-dimensional, because a triangle specifically is only able to be drawn on a board. I think it was Mr. Nathan who was correct in saying that one example would be a cube. And similar to cubes, three-dimensional objects are real-life objects. So now we will be learning how to describe things like this. So let's start first. We have a 3D object. Now, we said that a 3D object points in three directions. Like a shape, do you think that a 3D object must also have closed sides?
Depending on the object,
Yes.
sir.
It would be yes. Yes, because when we say that it must be closed, what I mean is that if we look at ourselves, our bodies, we can draw around our bodies a perfect border like this. Roughly. This is roughly an outline of my hand. And we can take this outline in multiple directions. So this is my hand from top down, and this is my hand from the side. We cannot say that a form will have a missing space here, because if it did, then that means that my arm wouldn't be a closed object. It would be open, and that doesn't make sense because everything has an outline. If we were to think about it as if we were to have a cube or an object like an eraser, we can't just chop off a bit of the eraser and draw it like this. We can't just say that there's no outline right here. We have to draw detail, and we have to show that if we were to, let's say, take a chunk out of the eraser, we have to draw that there is a border to it on the outline. It doesn't make sense that it would just be a little bit missing, because then it wouldn't be a real object. Does anybody have any questions?
No, sir.
No, sir.
Very good. So, a three-dimensional object has a specific name in math. We established that whatever it is must have closed sides and points, and it must have three directions. We call these 3D objects, form. So this is the 3D version of a shape. In math, we have to be specific in saying that a shape describes a 2D object like a square, while a form is a 3D object like a cube. Now, some people might say that something has a certain shape when it's 3D. When people say that, they are focusing on a specific aspect of the form. Let's say that you have like a computer screen. If you have a computer screen or just a computer in general that looks like this, and you have your little keyboard here, we say, what is the shape of the computer when you look at it? Well, the shape of the computer, it's like a square. That's what it looks like. When we say that it looks like a square, we are saying that because we are looking specifically at the computer screen and we are simplifying what it is. When we say that with a computer or a photo frame, or if we say it with a cylinder, kind of like this pen, you say, well, a pen is kind of round and circular because if you look at it this way and you move it around, it's smooth on all sides. We say in math that it may be circular when you look at it at a specific angle, specifically through the depth, but a pen is cylindrical because we have to describe it through its form. Any questions so far?
No, sir.
Okay. Now, similarly to how English tends to steal words from math and use it in confusing ways, pop culture does it often too. Like how before I said pop culture often confuses what a dimension is. Now, if you watch science fiction or fantasy, you have heard of something called a shapeshifter. A shapeshifter describes some kind of being, maybe it's a human, maybe it's an alien or something like that, that can change its form to look a different way. Like maybe a human that can, like a superhero that can turn into animals, things like that. They call them shapeshifters in pop culture, when in reality, they should be calling them form shifters. Because when a superhero or something of the like shapeshifts or form shifts into, let's say, a tiger, some kind of animal, the way they say it is that they take the form of a tiger, or an alien takes the form of a human. That's how shape and form are often used in real life. You specifically say form when you refer to a 3D object, such as like a human being or an animal. That's what it means to be a form versus a shape. Any questions so far?
No, sir.
Okay.
Sir,
Yes?
sir, I have a question.
Yes, ask away.
So if they shape shift, they don't collect the DNA of that thing they shape into.
That's not necessarily what we're talking about. We're saying that you have a certain form. This would be what you look like. You say that your body has a form, and that's what you look like. If you change your form, like how a shapeshifter does, you don't change the shape of your body, you change the form. So you have a different 3D body instead of a shape. That's what we're talking about specifically.
Okay, sir.
Now, just before we go into the math of it, there is one other thing that you need to, that is important when we discuss forms. Forms in real life are complicated. If you look at forms from different angles and directions, they look at like different things. Like for example, we have our cube, which we draw this way. We call this isometric drawing because this is the way engineers kind of draw it, so it gives a lot of information. So if we look at it in this angle, we can easily tell it's a cube, just as if we were to, say, look at a pencil from this way. So it looks like a little kind of 3D. We say, we can recognize this, it's a pencil. But in forms, there are different ways of looking at it, because if you take a block such as this and you put it on a table and you look at straight at the block, it'll look like this. And you see it from this direction, and you would see it as a square. But the thing is, a square is a shape, and a shape doesn't exist in real life. This is a confusion because you cannot see the depth of the object behind it. So you lack the information to tell what this actually is. It could be a block, it could be a shape, or it could be kind of like this eraser where it's not equal on sides, and it could extend a million miles, but you would not be able to see it because you're looking at the form in a direction that would make you think it's a shape. So another way that engineers do it is that they look at the form that they're looking at, and they not only draw the form in this way, but they draw the form as you would see it in other directions. So this would be when you'd see the form in this direction. Let's change the form that we're using from a cube, and we say that it's a lot longer than a cube. Let's say that this is what we're working with, so it looks similar to this eraser. We would say that this is the cube when you look the form when you look at it diagonally. This is the cube when you look at it from this way, or the form. This is the form when you look at it this way, and this is the form when you look at it this way. Does that make sense, everyone?
Yes, sir. Yes, sir.
So if we put our little markings here, here, and here, this is important. So if we did it similarly, let's take a pencil. We'll draw it like this. Can anybody tell me what would the pencil look like if we looked at it from this direction? How about Ms. Alicia? If we looked at a pencil down the tip, what would it look like?
Excuse me, sir. Can you please record the question?
Very good. Very well. So here is a drawing of the form of a pencil. This is the way we would draw the pencil in 3D. What would the pencil look like if instead of looking at it this way, we looked at it this way, down the tip? How would we draw it? What would it look like?
Sir, I don't know.
Okay, that's fine. So let's use an example. This looks a little bit like a pencil. So if we are going to look at it down at the tip, I'll point it at the camera. This is what it would look like. What does this look like?
Sir, it
Like
look
a
like.
cylinder.
Mrs. Alicia?
Sir, it look like a cone.
A what?
Cone.
A cone?
Cylinder.
A
Or a
little bit.
cylinder.
I'm sorry?
Or a cylinder.
Maybe. But what two-dimensional object does it look like?
Sir, I don't know.
A circle.
A circle. Yes. So it does look a little bit like a cube. I mean, it looks a little bit like a cylinder or a cone. It looks a little bit like it because you can see a little bit of light reflecting off of it, and humans have depth perception. So it looks a little bit like a cone. But the main idea I was trying to get across was that if you looked at it this way, then it would look like a circle. Just doing it. And if you wanted to put a little detail, here would be the tip. So in this sense, it does look like a cone because you might be able to tell that the pencil's coming up. But it does, but the idea is that it looks like a circle when it's going down this way. What would the pencil look like if we looked at it from this way? Anyone? So it would roughly be in this direction. What does it look like?
Like a cylinder.
Sort of like a missile.
All right, yeah. Not quite. The idea is that because because we're people and we have the eyes that we do, we can look at something from a certain angle and we can tell that it's a three-dimensional object. But I'm specifically, when we look at a form from different angles, a form may look like certain shapes. So what I'm trying to get across is, what does this look like as a shape from this angle?
A rectangle, a skinny rectangle.
Very good. So that's what I'm trying to get across. If we look at it from this angle, it will look like this roughly, and maybe a tip. But the idea is that we're looking at a cylindrical kind of structure. So it would look like a rectangle, and it'll probably have a little tip on the end. If we looked at the shape from this angle, then what would it look like? So before we looked at it from this angle, now let's turn it 90 degrees. What does it look like now?
The same thing, sir.
Exactly. So it would look like this, kind of. The reason why is because a circle is symmetrical, which means that if you look at the circle from left to right or up to down, the circle would look the same from all sides. And because a cylinder, or in this case like a pencil, is built up of just a bunch of little circles, that means that whichever side that you look at it along this way and this way, so from here or to here, it would look the same in this way. It is only when you look from the top down that it looks like a circle. So this is, in a way, how forms work. A form is a bunch of shapes copied in a certain direction. So take a cube. Let's go back to a cube. If we take a cube and we said that a cube is like a loaf of bread, we can take a knife and we can cut the bread so that it is now a smaller cube and another cube. Ms. Delana, we are saying that from the way that we look at the forms, we can see that a form is, in a sense, just a bunch of shapes copied in a certain direction. So in this case, I'm talking about loaves of bread. So a loaf of bread is kind of like a cube. So what we can do is we can take a knife and we can cut the bread. So now we have another cubic form in a bigger cubic form. If we keep cutting this cube forever, we would eventually get a square, where the square has no depth. It no longer points in this direction like how this smaller one does. And because of that, it is, in a sense, a shape. So we can take a bunch of shapes and we can copy them over and over again, and we say that this is just a bunch of squares stacked on top of each other. Does everyone understand?
Yes.
Here's another example. This is a notepad. A notepad is kind of a rectangular cubic shape, like a prism. If you see, the notepad is simply a bunch of paper stacked on top of each other, and paper are really thin, so they're kind of like rectangles. So it's a similar concept here. You take a bunch of squares or 2D rectangles, and you stack them on top of each other, and you get a 3D shape like this. So that's what forms are, in a sense. And if we apply it back to the cylinder kind of example, if we just use a normal cylinder, we could say that a cylinder kind of like a length of meat, like in a sausage kind of shape. You slice up the meat into many segments into little circles. So a cylinder is, in a sense, a bunch of circles stacked on top of each other. Any questions?
No, sir.
Very good. So this is us talking about the forms in a verbal kind of way. I would like to take a 5-minute break. So we'll get back at 2:08, and then at 2:08 we can talk about the actual math behind the forms. Does that sound good, everyone?
Yes, sir.
Okay. I'll see you all at 2:08, 2:09. I believe there is a little bit of internet issue. Okay, it's 2:10. I understand some people had internet connection issue if they join back. But we will continue on. Is everyone here?
Yes, sir.
Okay. Mr. Aryan, Mrs. Marks?
Yes, sir.
Okay. I'll assume Mr. Aryan is here. So we just described form in verbal ways. We talked a little bit about what they looked like and sort of how they worked, but the important idea is to understand the math. I believe that is Mrs. Ariel. We are now going into the math section. So we know that our forms are three-dimensional or three-directional. We described this earlier in geometry by saying that a line is one-dimensional, and with a line, we describe length. We say that a perimeter or a side has a length of a certain amount, and we clarify it with units, such as a centimeter. And we say that a line describing a length, let's say 2 centimeters, is centimeters to the power of 1. And this one, this exponent, describes the amount of directions. So because it is a line describing a length, it is a length of 2 centimeters to the power of 1, or this. We also said that when we describe a shape is different from a line because a line has length. But a shape has area. And an area of a two-dimensional shape, let's say if this line was in a square, pretend that this is a square, not a rectangle. We say that the area is 2 centimeters times 2 centimeters because it is side times side is a square. So we square the length to find 4 centimeters squared. The square describes 2 dimensions of length and width being the same. So it is 4 centimeters squared, or 4 squares of a centimeter squared each. That is how we define area. Length is in terms of the amount of lines of our unit. So 2 centimeters of length describes a length of 2 of centimeter lengths. So this is what you have, a centimeter and a centimeter. A centimeter squared describes 4 squares of area centimeters squared. I don't know how visible it is, but I think you get the idea. So now with 3-dimensional shapes, I think you get the idea that instead of centimeter to the power of 1 or 2, now we have centimeters to the power of 3. Can anybody tell me if our length in centimeters to the power of 1 is lines and our area of centimeters squared is squares, what would centimeters to the power of 3 be? How about Mrs. Ariel? Mrs. Ariel, do you know what we call it when we raise something to the power of 3?
Not sure, sir.
Sir,
Okay.
I know.
Okay, Mr. Nathan, what would it be called?
Volume.
Well, not necessarily that I was asking, but it is true that instead of length or area, we describe volume. Would anybody other than Mr. Nathan know what it's called when we take something and do the power of 3? When we do it to the power of 2, we called it squared. So what would we call to the power of 3?
Square root.
Sir, Q.
Very good. Not quite, Mr. Aryan, but you have the right idea. It is to the power of 3, which we call cubed. So to the power of 1 is just the length. To the power of 2 is squared because it describes square area. When it's the power of 3, we call it cubed because it is 3-directional, whereas a square is 1-directional. So we found that we could find our area by taking our original length and raising it to the power of 2. So if we know that the length or volume or area can be found by taking our length and raising it to the power of either 2 or 3, what would our volume most likely look like? How about Ms. Ariel?
Sir, could you repeat that? My internet is breaking up.
That's fine. Mrs. Ariel, when we find our square area, we said that our square area, because a square is a length squared, or in other words, the length to the power of 2, which is squared, could we find our what we call volume by taking our length and raising it to the power of 3?
Yes, sir.
Yes. Mrs. Ariel, do you know what 2 to the power of 3 would be?
6, sir.
Not quite. It is 2 times 2 times 2. Can you do this, Mrs. Ariel?
Sir, 8.
Very good. It would be 8. So length is our 2 centimeters to the power of 1. Area is our length squared. So volume is our 2 centimeters cubed to the power of 3. So the equation of a cube, we can say that the volume of a cube is equal to the length to the power of 3, because we are taking our length and we are pointing it in 3 directions. Any questions so far?
No, sir.
No, sir.
Okay. So when we say, when we use our length for a line, it was just length because it is one direction. When we say shape, we said length and width. Or in other ways, we would say base and height, which I personally prefer. But now that we have 3 directions, we have 3 names for our directions. We have our length, or base. I know many people say base. We have our height, and we have what we call depth. So this is what we are using: base, height, and depth, or length, height, and depth. Let's erase this, make a little room. So we describe the volume, where volume is the amount of space that a form takes up. I would like to point out that this is not how much of a form there is. It is merely the amount of space that the form takes up. A good example of this would be a volleyball. A volleyball versus a boulder. If you have a volleyball that was equal size to a boulder, they would have equal volume, but they would not have the same amount of material in it. The amount of material in a form refers to something else, but a volume describes the amount of space it takes up. So volume can be hollow. So volume is how we described before: length cubed, or if we use our terms, it is base times height times depth. So volume describes the amount of space the form takes up, and we represent it in length cubed in the instance of a cube, or our base or length, our height, and our depth. Now, a good way, when you think about a form and you think about it in terms of length and our height and our depth, it's good to understand how each of these terms apply to it. So the most confusing one is usually depth. And there's a certain reason why, because when you draw a graph, as we know, as we did before, we drew it as y and x, where y is our height and x is our length. So in other words, we want to draw it as this way is height and this way is length. Let me just quickly make sure about something. Okay. So that is what our 2D graph looks like. H and our height and our length. When we draw a 3D graph, we do it differently. Let me move this. So we don't have to say base, we'll just say length for simplicity. Length, height, and width. No, wait, did we say width? No, we said depth. If you remember, the way we drew, the way you always see cubes drawn is like this. Now we can tell that a cube has the direction this way for the height, and we can tell that it goes this way for sort of the base. And in this way is the important one for 3D shapes. This is depth right here with how we drew our cube. So in a graph, a 2D graph, when we drew it like this, we drew it in accordance with a square. With a 3D graph, on the other hand, we draw it in accordance with a cube. So these are the 3 directions that you normally see cubes drawn in. So if we incorporate these 3 axes, the axes we drew here, into a graph, we have up and down, we have, there's a little bit of an artsy way that you might like to draw it sometimes, where you're at 0 and you draw little broken lines to look like it has depth. And then you have this way. So it's our top down, our left, right. And our depth goes this way. So this is what our graph will look like. Any questions so far?
No, sir.
Okay. So a little similarly to how with this graph, you see how if you look at the outsides of the graph, it looks like the corners of a square. This is sort of the same idea because the corners of each of this graph kind of look like cubes. So you have this little bit, this little bit, this bit, and there's like 8 of them. But the way we have these is that we have our Z, our X, and our Y. And there's a very particular reason that we write it this way. We draw our graph this way. We will not necessarily be going into graphs much from now to December. This is just a sneak peek at what you'll be going through in the future. But I just wanted to show you this. So the way it is that Z describes our depth technically, but because it is pointing up on the board, we say that this is height. And then we have our X and our Y. All right. So if this doesn't look like it makes a lot of sense, it's understandable. I know people in college who still think it's ridiculous, but this graph shows depth really well. So what I'd like you to do is that I'd like you to draw a regular graph on a piece of paper. So like this little XY graph we have here. Okay. Everybody understand?
Yes, sir.
Okay, I'd like you to draw an XY graph like this. Does everybody have it? Hello?
Not as yet, sir.
Okay. It's just a simple vertical line and a horizontal line. This right here.
Finished, sir.
Okay. Everyone else got it?
Yes, sir.
Okay. Mr. Aryan, I'll assume you have it. So everybody has their little piece of paper with their graph on it. Now, I want to make sure that you have it laying down face on the table. And what I'd like you to do is put your pencil or whatever you're writing with where the Z line should be. Now, if we think about it, our piece of paper, or in this case, my whiteboard, is a square. And if we add a third direction on your piece of paper, where would it go? You have your piece of paper laying down on the table. Here, like this. Here is our Y, and here is our X. This is what you should have. Now, think about it this way. We have our graph. we see that we have a y direction pointing this way on the table, and we have an x direction pointing this way on the table. So it goes this way and this way. If we think about what a third direction will be, it can't be in a direction on the paper or whatever, or this little board, because directions like this are just directions in this way and this way. So that means that if it can't go in this direction or in this direction, that means the only direction left that's not this way or this way is up and down. So this is what your pencil should look like. Does this make sense to everyone?
Yes, sir.
Okay, so all of you have your pencils like this?
Yes, sir.
Okay, your pencil is the z-axis. So this is the direction that the z is pointing in. And what this refers to is depth, because you can't have depth on paper. You can only draw it in either in these directions. Depth refers to the ability to how far into the paper it goes and how far out of the paper it goes. That's what depth is. Height, when we draw it in our models, when we draw our height in our models, we draw it going up and down on our paper. But depth would be like if you're looking at it from a distance. So let's say you're looking at a car. So you're like over here. This is what you see. You see a car driving in this direction. So in your model, that'd be Mrs. Ariel. So if you're far away and you're looking at a car driving in this direction, you can see that the car is driving in this direction here, and you can see that this vertical direction would be the height. In this case, the depth, as we did here with our z-axis, our depth would describe the distance from us to it. So that's what depth would be, because the depth would be the distance that you are if you saw this from you to the car. And that's how we draw it in our models. Now, if we look back to what we have here on the board, we have our z-axis going up, our y-axis going to the right, and our x-axis going this way. If we take our x, y-axis, our little graphs, so here's our x and y. We can see that the 3D graph, the z, x, and y, is that we take our graph, we have it flat on, and we point it in this direction. So the x is in this case the depth because it points towards us. The y-axis points this way because the height, and the z-axis is on top. Does that make sense to everyone?
Yes, sir.
Okay, good. People often have trouble understanding this. So this is how people do it in 3D models. So Z is what our new height would be like. Because if you want to have a 3D model, you have a little platform that you put little buildings on top of, and the buildings have a certain height. So if we have it in the context of this eraser, we have the height of Z going up and down. We have the length Y from this way to this way. And we have the depth, which is this way to this way. So if you didn't fully understand it, that's okay, because this isn't really necessary to what we will be going over later. But does anybody have any questions?
No, sir.
Very good.
Sorry, sir, my internet is going on and off.
That's fine. Did you see how we compared the 2D graph to the 3D one?
Yes, sir.
Okay, so you saw that, so we have our X and Y, so our Y and our X, and this 3D graph is, we just take our graph and we put it on the ground like this, so our Y goes in the direction, and our X is the depth, and our Z is the direction up on top. So if you didn't completely understand this, that's okay. This isn't really necessary to what we're doing, but it is just me showing you what you'll be doing in the future. Not in my class, but in like college. But if we go back to what we were talking about with forms, we have our volume, which we described. It is the space that the form takes up. So we have like a beach ball, for example. Even though the beach ball is hollow, it still takes up a certain amount of space, and that would be our volume. And we would measure it. Now, a volume is how much space it takes up, but oftentimes what we want to know is how large the surface of a form is. So if we have our eraser, we can say that the eraser is a certain volume, so we know all the measurements, but let's say we wanted to take the eraser and we wanted to put it in a hole. Think of it like blocks. You know, those toys where it's like a board and there are certain hollow shapes that children take blocks and they put them through, whichever the correct shape is. So think about this toy. If we look at the toy from top down, we can see that this is what the toy looks like basically. So it is just a board with 3 holes in it. So we have square, circle, and star, for example. A shape has to have the correct side, the correct surface to be able to fit through the holes. Does that make sense so far?
Yes, sir.
Okay. So let's use this this block, for example. So this block, let's say, this square is a 2x2 shape. We don't have to have units for this example. Can anybody tell me what this area of this hole would be? Anyone, the area?
Oh.
I think you said 4. 4 would be correct. So this hole, from looking at it top down, it would have an area of 4. So think about the toy. If the toy is just from top down this, and the hole has an area of 4 in a square shape, that means that whatever form, like a block, for example, that passes through this hole must have on the outside a shape of this square. So for example, let's use a cube of 2, 2, 2. Before, we said that when we look at a cube from a certain angle, like this one, it would be like a square of 2 by 2. Does that make sense to everyone?
Yes, sir.
Okay. So we said that this cube, when we look at it from this way, has an area, or it looks like a square of 2 by 2 in this case. So it would also have an area of 4. And a cube, we said earlier, we could chop it up into little slices like bread, and it's all just a bunch of squares of 2 by 2. So that means that the squares of 2 by 2 will fit into this hole. So that is how this block toy works, because throughout the square, it always has an area that can fit into this hole. That means the whole block will go into the hole. Now, can somebody tell me if the block was extremely long, like that, but it still had the same surface, would it be able to fit through the hole?
Yes, sir.
Why?
Because the length just some more.
Correct.
The width stayed normal.
Yes. Correct. When we look at this extremely long rectangular form, it'll still look the same, like this square, when we look at it. So because it still looks like it from all the way, and throughout the whole length of the rectangular form, it's still a bunch of little squares of this same shape. That means this entire thing can fit through the square. So Mrs. Ariel, we said that because if we took a rectangular form such as this, where it was very long, but the area of the square, when we look at it this way, is still 2 by 2, the same as the hole, we can still fit the whole form through that hole. Does that sound right?
Yes, sir.
Good. So this is what we call surface area. Can anyone guess what surface area is by the title?
It is the area of all the sides, all the base.
Very good. So when we say surface area, we go back to the notion of area, where area is the amount of flat space that a shape takes up. When we say surface area of a form, well, it says surface and area. So the area of the surface. So we can take the area of the sides and we measure them and we say that the surface covers this amount of area. In this case, we can take the surface area of just this little part of the form and we say that because the form always has this area throughout the whole depth of the form, that it can fit through this little hole. That is how the surface of a form works in a sense. And surface area can be adapted in many ways. So let's remove this. And instead of that, we have a square pyramid. So we have a square pyramid of some height. We say that this direction is it has some depth. So some depth pointing this way, but it has a base because it is a square pyramid. It has a base of a square, and the square is a base of 2 by 2. If the base of this pyramid is a square of 2 by 2, does it look like this? Mrs. Ariel?
Sir, could you repeat the question?
Very good. If we have a square pyramid, right? So it looks like a pyramid. And if it has some depth like this, but the base of the pyramid is a square of 2 by 2, so it looks just like this, right? So this is the base of the pyramid. Would this pyramid be able to fit into the hole?
Yes, sir.
Can you tell me why?
Because it's just like the cube.
Very good. So this describes surface area when you look in a direction. What you can do is that you can look at the pyramid from at the base, and you can just measure the base itself. Or you can look at the pyramid through the tip. Goodness. So this is similar to what we said before with the pencil. If you look at it through the tip, it looks like a circle. Similarly, if you look at a square pyramid through the tip, it looks like a square. And this is how you can measure the surface area of the square pyramid through looking at a certain direction. And by that, we said that the pyramid, when you look at it through this direction, looks exactly like the cube that we had before. When you looked at that cube in a certain direction as well, they have the same surface area from looking at them through these directions. And because they have the same surface area, and the cube can fit into the hole, and the hole has the same area as both the cube surface area and the pyramid surface area, both the cube and the pyramid can fit through the square hole. Any questions?
No, sir.
Okay, we'll continue this next week. All right. Does anybody have any other questions before we end class?
No, sir.
All right.
No.
Very good.